Here we go. All right. So we have of course fallen behind as a result of our snow days. Let's take a look at our schedule. The super updated update to the schedule. Right, so here we are today on Friday. Campus is open again, finally. So we missed the quiz. That's going to happen on Monday. So the quiz on Monday. Okay, quiz will be held Monday, February 27th. We were going to have 2 days of 4.1. Instead, we're having 1 day of 4.1. But as you'll notice up here, I did put this link. Why is it cut off on the side there? There we go. I did provide this link to a video playlist. I have all these video playlists that I haven't really been using, but I should probably use more. I recorded these a year ago, 2 years ago, maybe. So these first 4 videos are about related rates, which is the first topic of chapter 4. Did you folks get a chance to watch those 4 videos? Can I see like a show of hands, kind of, or a thumbs up? Some sort of a... Okay. Thumbs down if you didn't. Okay. So what I think I'll do today is I'll do a couple more examples of related rates problems. Okay, we'll start with one example with a triangle, and then we'll do another example with like a 3-dimensional shape. So I'll do like a basic example and a medium example, or a spicy one. I don't know if it's medium or spicy. Kind of all of these problems are pretty hard. Related rates problems tend to be quite a challenge, and I think that students find this is one of the more challenging sections in the class. Section 4.1. Okay. So before I begin, let's review DREADS. DREADS is an acronym for a particular strategy that we can apply. It's like a very sort of organized approach to solving a related rates problem. First of all, you draw a diagram. It is really helpful to draw a diagram and label in that diagram constants and variables. Okay, then you identify what the rates are. Then you set up an equation. You differentiate it. And in related rates, we're always talking about things changing over time. It's a very specific application of derivatives. Things changing over time. So differentiate with respect to t, time. That's technically implicitly, because you're almost never going to have t as an actual variable involved in your equation. It's about other variables, but all of them are thought of as functions of time, like independent, separate functions of time. So then what we do is we substitute in any specific values we're given, and then we solve for the desired rate. Okay, so example. Let's suppose we're going to do a ladder problem, similar to the ones in the videos, but not exactly the same. Let's say a ladder is leaning against a wall. suddenly the ladder begins to collapse. You guys have probably used a ladder before. Some ladders are just solid, but other ladders have like sort of two parts, you know, like a
You can fold them out to make them taller.
or not fold, but like slide.
Okay, yeah.
You know what I mean?
Yeah.
So then what I'm imagining here is that the ladder begins to collapse in on itself, so it gets shorter.
They should have locked it.
They should have locked it, right? So that begins to happen. Then what we can say is as this happens, I should specify here what's happening here. What's moving? The base of the ladder remains in place, but the top slides down the wall. Okay. If the ladder is collapsing, if the ladder's length is decreasing at some specified rate, we'll say 1 foot per second, or maybe 1.5, just so we have something besides 1 to plug in. That might be a bit confusing. 1.5 feet per second. Okay. And this is the sort of question we always ask in a related rates problem. It's like, if one thing is changing at this rate, how fast is another thing changing? So let's say, how fast is the angle between the ladder and the ground how fast is that changing when what? And we need something to specify. We need something to specify this this like moment in time. Maybe when the ladder is 6 feet long. Okay. Okay. I think I just realized I need to add in a piece of information right up here. Let's say that the base of the ladder is 4 feet from the wall. Okay, I think that's a crucial piece of information that I left out. All right, so now let's start drawing a picture. Now that we've written out this problem, we're going to draw a picture. So first step, D, diagram. Okay, so for my diagram, I'll draw a wall and the floor or ground. We'll put the ladder in there. So the ladder is like this. The ladder is leaning against the wall. Okay. Now, this is a constant angle of 90 degrees between the wall and the ground. We will always be assuming that things that you expect to be vertical and things that you expect to be horizontal are vertical and horizontal. So like walls are vertical, the floor, the ground is always horizontal, that kind of thing. The surface of water is horizontal. So So just like always, we can always assume those things. All right. So now we want to identify what variables and constants are involved in this problem. Okay. Right here, I provided this. This is a constant. The base of the ladder is 4 feet from the wall. And it says down here that the base remains in place. So when I said this, that's related to this piece of information, that the base remains in place. So this distance from here to here is 4 feet, and it's not changing. So this is an example of an actual constant. You can label that in your diagram as a constant because it's not a variable. But there are other things in this problem that are variables. So for example, the top, so first of all, the ladder begins to collapse, which means that its length is decreasing. Okay, so the length of the ladder, which we'll call capital L, that length is a variable. So I can't like label the ladder's length something, anything in particular. It's at the end we're asking like when the ladder is 6 feet long. So that's a particular value of L, but it's preceded by the word when, which is really important. Okay, because it means that it's just like a moment. It's just sort of identifying a moment in time. It's not telling you that the ladder is 6 feet long, period. It's saying when the ladder is 6 feet long, how fast is this thing moving or whatever? Like what is this other rate? Okay, so that's not, we can't label 6 feet in our diagram. What else can we label? We might want to label the angle, because the angle, how fast is the angle between the ladder and the ground? Is that going to be a constant or a variable? Well, we're asking how fast it's changing, so it indicates that it's probably variable. And it makes sense that it would be variable, because what's going to happen as the ladder gets shorter, right? In our diagram, we can kind of imagine what happens as the ladder gets shorter is the ladder is going to sort of slide down the wall like this, like it's going to sort of pivot around that point right there. And the top of the ladder will slide down like that. Okay, which introduces our last variable we can label in here, which is the height of the ladder. So let's make that like purple over here. That's the height. This distance right here. The top slides down the wall. There we go. So that's also a variable. Okay, so almost everything's variable except for that distance between the wall and the base of the ladder. That's fixed. All right. Any questions about the setup so far and the diagram? We doing okay? Okay, I got a little bit of feedback there. I'm going to move on. Our next thing to do is to identify the rates. So looking back at our written problem, there is one rate that is provided, and it's this rate over here. It's the 1.5 feet per second. That's the rate at which the ladder's length is decreasing. So what I want to do is I want to represent that in the form of a derivative of a variable. So looking back at the various variables that I introduced in my diagram, I need to identify which variable is at the rate of change in. It's the rate of change in L. So what I can write is I can write dl over dt. Okay. all of the rates that we deal with are going to be derivatives with respect to time in this type of problem, okay, in section 4.1. So dl over dt is what we'll call that rate, and we can say that it's equal to 1.5. Although, because it is decreasing, it's getting smaller, right? We want to make that negative 1.5. And I'm not going to bother with units at the moment, okay? The way I tend to approach these things is I tend to approach them without dealing with units until I get to the end. So I just sort of treat it as a math problem without any units. And then at the end, we can go back and figure out what the units are supposed to be. Okay. You can use the units the entire time, but it has the potential to get confusing if you do that. So just be warned. So there's always going to be at least two rates that we want to identify in this step. One of them is the rate, at least one of them is a rate which is given. Sometimes you're given more than one rate, but then there's always going to be some rate that we're looking for. So in this case, the question at the end here is, how fast is the angle between the ladder and the ground changing when the ladder is 6 feet long? So how fast is that angle changing? That's the other rate we want to identify here, and it's the rate of change in this angle, which I called theta here. So d theta over dt. And that is the one we don't know. That's the one that we're searching for. Okay, so this sets up our goal for the problem. Okay, that is the goal for this problem, is to calculate that length when L equals 6, and that comes from when the length of the ladder is 6 feet. Okay, so actually I would say I like to put this information in, like I like to write it right here in my rates step, because I just think that's a good place to put it, right? When you're, because the rate step is kind of about setting up, here's the information we have and here's the information we're looking for. Hannah makes a great point in the chat here. If we were interested at all in this other angle up here, then since the bottom one, theta, is decreasing at 1.5, no. Oh, no. Okay, never mind. Hang on, back up. The negative 1.5 is the rate of change in the length, not an angle. And whether we're looking for, it doesn't matter which angle we're looking for. If we were looking for this other angle, that doesn't change the fact that the L is decreasing. So the rate of change in L is negative 1.5, and that's negative. We're not going to change that just by switching our perspective to a different angle. But we do want to consider whether we should expect our answer to be positive or negative. Based on your physical intuition here, do you think that theta is going to be getting smaller or getting bigger? We have a situation in motion as the ladder slides down the wall. Is that angle getting smaller or bigger?
Smaller.
Yeah, great job. Good, you guys. Yep, we should. So I'm going to write here, just as a note to myself, expect negative. Okay, we should expect a negative answer. If we get a positive answer, then we can go back and see if we made a mistake somewhere. Okay. So let's move on to our next step, which is to identify the equation we're going to use for this problem. Okay. In some related rates problems, you're like given an equation, handed the formula or whatever, like directly. But in a lot of them, like this one, we have to kind of figure out what we're going to do. So, we have, let's look at zoom in on our diagram here. We want to come up with an equation that involves certain pieces of information. We want to make sure that our equation involves the rate. No, do this. We want to make sure that our equation is going to involve the variables, both of the variables whose rates we identified in the rates step. Okay, so we got to make sure that our equation involves both L and theta.
Would it be inverse cosine to get the theta, or would it just be like cosine because it's adjacent over hypotenuse?
We could do it with inverse trig functions here, but I'm going to show you guys how to do it with a regular trig function because you don't need to do it with an inverse. Does that make sense? We might use an inverse function to solve for something later, but when it comes to the derivative step, you don't need it to be an inverse because we're going to do it implicitly anyway. So might as well stick to regular trig functions. But I think you are right, though. You said cosine, right? Okay, so Rowana suggested we use cosine. Cosine would use the angle, the adjacent side, and the hypotenuse. Why did you pick cosine instead of like sine, for example?
Because you did it in the other videos.
Oh, I didn't do this problem, did I? Didn't I do a different
No,
one?
you did. You did something the same where you used cosine to get theta.
Oh, sure.
So that's all I remember.
Okay, sure. I think in the other one, the L was constant. So this is a very similar problem, but I switched which one was constant. Now the base is constant, and the hypotenuse is the variable. Okay. So okay, let's not have that be our reason. We don't necessarily always want to use the same trig function because it does depend on the situation. So so first of all, why are we using trig functions at all? For those who didn't watch the videos, it's because we want to get some sort of an equation that involves the angle as well as some of the sides of the triangle. Trig functions are the perfect way to do that, right? So let's write down a few candidates. Cosine of theta is adjacent over hypotenuse. That's 4 over L. Sine of theta is opposite over hypotenuse. That would be h over L. And tangent of theta is opposite over adjacent. So that would be h over 4. All right, so of these 3 candidates, which one, can we rule any of them out? Or which ones would we prefer to use?
Would we not do sine because it doesn't have the constant in it?
Ooh, there we go. It makes sense to use the constant because we have it. As long as we have a constant, we might as well use it because using a constant in our equation is going to make the derivative of that equation easier to compute. Right, so that's one of the things I say in the videos as well. For those who haven't watched it, is like take advantage of constants when you have them. Okay, so yeah, I agree. We'll rule out sine because it doesn't use the constant. What about cosine versus tangent?
Would we want to rule out tangent because it doesn't contain the L, and the L is what the variable is dependent on?
Or rather, maybe not dependent, but like it's the one we know something about. So let's use the one we know about, right? Like this is a valid relationship. If we had instead been given some information about H, then this would be the one to use. But since we were given information about L, we don't want to use an equation unless it has L in it. So yeah, so there we go. So that gets us down to just cosine. All right, so that's going to be our equation, folks. Cosine of theta equals 4 over L. So now that brings us to the next step after equation. Let's see, we've done this, we've done this, we've done this. Now we differentiate implicitly with respect to t. Next B. So the derivative of cosine is negative sine, right? So I'll begin with a negative. Here, actually, maybe let me go a little slower here. Derivative with respect to t of both sides. That's what we're doing here. And so this is an implicit differentiation with respect to a variable that doesn't even appear anywhere in the equation. That's all right. It just means that this variable theta and this variable L are functions of t, and we treat both of them like functions of t. So what we did for y in implicit differentiation before, we're going to do now for both theta and L, which means we have to multiply by the theta prime and by L prime. Or theta prime and L prime, those are the rates, dl over dt and d theta over dt. So those rates are going to show up through the implicit differentiation we're about to do. And they'll end up in our equation. All right, so on the left side, we do the derivative of cosine, we get negative sine. Right? Then, because that was a function of theta, and theta itself is implicitly a function of time, we multiply by the derivative of theta with respect to time, which we just represent by its name, d theta over dt. There we go. So that's the left side. And on the right side,
Wait, I have a question.
Oh, sure.
So are you using d theta over dt in replace of y prime? So like so would it technically be theta prime if you think about it like that?
Yeah. If you're using the Newton notation, it's theta prime. In this context, I like to make very clear that all our derivatives are with respect to time, and so that's why I'm using the Leibniz notation, because it's got the dt to tell you Remember, I think I've kind of mentioned this before, that Newton notation and Leibniz notation are interchangeable, except that the Leibniz notation is a little more explicit about what's going on. It's telling you what the derivative, what variable you're differentiating with respect to. How are you measuring this rate of change? What is it? What are you measuring against, right? And it's we're measuring against time, right? How fast are we changing per second, not per something else? We're not, you could also have a rate of change in theta with respect to this other variable, but that's not what we're talking about here, right? So this is more explicit to be very clear about what's going on. And so I prefer to use that notation in this context. That make sense?
Yes, thank you.
Cool. You're welcome. So on the right side, we want to differentiate 4 over L. What differentiation technique can we use to differentiate 4 over L?
Would you be able to do 1 over L times 4?
Sure.
And then take out the 1 over L, if that works? Or no, because in the constant, you still want the constant. Never mind. Yeah.
Take out the 4.
That makes sense. Okay.
Constant multiple rule. So there's a constant multiple rule. That's good. What about differentiating 1 over L now?
Quotient rule.
Ooh, we have a vote for quotient rule.
I was thinking of making L power -1 and then using the product rule. Not the product rule, but the power rule.
The power rule, yeah. So there we go. So we had 2 suggestions. The quotient rule, because it was 1 over L, a fraction, but also 1 over L is just L to the power -1, Julia points out. So we could just use the power rule. My preference is to go with Julia's strategy here and just treat it as a power function and differentiate it with the power rule. If you do the quotient rule, in my opinion, you're doing more work than you need to. It's gonna work out, it's fine. You have to remember that one of the functions you're differentiating is a constant, because your numerator was 1, so that's a constant. You can do the quotient rule, you will get the right answer, but I think you're doing about twice as much work as you need to in this part, in this step right here. So I'm going to differentiate that with the power rule here. So bring the -1 power down, we get -4, and now we have L to the power -2. And then, because it was L, we multiply by dl over dt. There we go. And I guess I'll just copy the other side. All right, there we go. So now we want to solve this for, well, actually, we could, I guess it doesn't matter. The last 2 steps, the substituting and the solving, can be done in sort of either order. Doesn't really matter. So S and S is substitute and solve. So we want to substitute in some information. Okay, now that we've done a derivative, now we can like zoom in on a particular moment in time identified by this when. Okay, the word when is very key here at this moment because we've done our derivative, we've got the rate, we've got this new equation this new equation here that like involves the variables, but also their rates of change, right? Now we just want to substitute in everything we know and solve for the one thing we don't know yet, which is d theta over dt. Okay. So yeah, so let's go ahead and put in everything we can. On the right side of the equation, we're going to have -4 times 6 to the power -2, and then times -1.5. That was the rate of change in L. On the left side of the equation, we have d theta over dt, and then we have negative sine of theta. Now, that's substituting in, so far I've substituted in L equals 6, and dl over dt equals -1.5. Our goal, remember, is to solve for this guy, d theta over dt. But that leaves negative sine of theta. That's a problem. We need to know what negative sine of theta is. We need to be able to substitute in something constant for that so that we can get our final answer. So we can get a constant answer, right? We need to get a number.
We have, can we use the ladder 6 feet long and then do sine of theta, which is no cosine? Never mind. That'd be
No,
cosine.
you're onto something. You're onto something. So over here, this diagram here, there's a particular moment in time when L equals 6, when we have triangle 4, 6, theta's down here, right angle, and here's H. What can we do?
We can solve for h using the Pythagorean theorem and then do
There we go.
sine of theta.
That's right. We can solve for h using the Pythagorean theorem. So we know that h squared plus 4 squared equals 6 squared. Here we have h squared plus 16 equals 36. So we subtract that 16 and we get h squared is 20. So h is the square root of 20, which should be like 2 times the square root of 5, I think. Okay, so that helps us to solve for h. So now we know h. Is that what we wanted? Or did I just do the wrong thing? Why do we want h?
Couldn't
Sine theta
you
is
do?
Let's hear from Boyd, and then we'll come back to Julia.
You could do arc cosine and find the angle with that. Could you not?
You could do arc cosine and find the angle and then substitute the angle into here. Yeah, I think that's where I was kind of going earlier, was like, I was saying, why did we find h? Because don't we want to know theta? So yeah, arc cosine is one way to do it, but I actually don't recommend doing that, because when you start dealing with specific values of angles, and if you solve for the angle and then substitute that in, you get into this tricky situation where the angle is probably an irrational radian value, and you end up like approximating it by just cutting it off after a certain number of decimal places. Maybe like that, students will tend to do that, and that can introduce error into the computation, and you get a less precise final answer because you rounded on the way there. You guys know about this sort of thing? Does your science professors talk about like this idea of like there's a problem if you have to round multiple times in the process of computing an answer, then you get compounding rounding errors?
So in your
but I remember
videos,
sig
you-
figs.
Sorry, Frowell, what was that?
I said no, but I remember sig figs.
Oh yeah, sig figs. I'm less concerned about sig figs and more concerned about this strategy of trying to round as little as possible. Boy, did you want to follow up on your?
Can we just do a simple equation on the calculator?
Well, calculators round as well. But you know, because they're not magic, they can't deal with irrational numbers either. But there's another strategy that doesn't involve any rounding at all, which is I think what Julia was getting at.
Yeah, so sine theta is h over L. So if we already have our h, we can do h over L, which will be that 2√5 over L, which is 4. And then we can just plug in negative 2√5 over 4 to our negative sine theta.
Yeah. Okay. Yes. Perfect. We're using our SOHCAHTOA, right? Sine of theta is opposite over adjacent. H over L. That's right. So we have what we have here in place of negative sine theta. I'm going to replace that with negative H over L. And then I don't have to do any rounding of, I don't have to do any arc cosine. I don't have to deal with radian values or any angle. Like all I have to do is put in negative 2 times the square root of 5 over 6. Like that. And that's times d theta over dt equals the rest of this stuff. So this looks like it's going to end up being 1/6, I believe, if we simplify it. Is that right? Because 4 times 1.5 is 6, and that cancels with one of the 6's in the denominator. There's 2 6's in the denominator. There's a little just, you know, arithmetic canceling of stuff there. Yeah, and then it looks like we're good to go. I guess we could multiply both sides by 6 and solve for d theta over dt, and our answer should be 1 divided by this numerator, negative 2√5. And then what we would probably want to do there is pull out our calculator and round once, right? Let's compute this answer and round it one time instead of having like a rounding and then more computation and then more rounding. So this is not significant figures. In my opinion, this is more important than significant figures. Let the science teachers argue with me about that. But I think that avoiding the rounding is overall, I mean, significant figures is just a matter of precision. Like you can get more precise rounding, precise measuring tools and get better significant figures. This is about your strategy, like how you perform your calculations, and I think that is a more significant issue here for us, especially if you're going to be like an engineer or something. What did we just get there? Negative 0.224. I'll round a little bit here to the nearest 3 decimal places. Negative 0.224. All right, what units should that answer have?
Radian per second.
Why? How'd you come up with that? You're correct.
Because the feet cancel out if you like write in all of the while you're doing your work, and then you'll have 1 over seconds, and then I'm pretty sure if you use like that's all I got. 1 over seconds, and then you plugged in radian without explaining it.
Radians are a unitless measurement. Yeah. So radians are technically a unitless measurement. If this is kind of what I said about it being confusing, if you keep the units in the entire time, because yeah, the feet cancel out. You don't have any feet around. You just have like nothing in the numerator. We have seconds in the denominator because we were dealing with per second originally. So the original rate of change is given feet per second. So we know we're measuring against seconds here. But yeah, the numerator has like no unit in it at all, and that's because it's radians. The rule of thumb is that we're almost always dealing with radians in calculus. If I ever give you a problem that uses degrees, your very first thing you should do is convert to radians and do everything in radians, because any computation done with degrees is going to have the potential to give you wrong answers, because the sine and the cosine derivatives, like here, like this part right here where we did the derivative of cosine is sine, that depends on theta being in radians. If theta was in degrees, that derivative would be different. So just the very fact that we're using this derivative rule means we need to be working in radians. So always radians. All right, so there's our first example, and that took us a little bit longer than I was expecting. I spent more time on that than I meant to. That's okay. We can start another example, and then you guys can work on it over the weekend. We're just gonna play it by ear. We're behind now. That's all right. We'll catch up next week. The main focus for you over the weekend should probably be preparing for the Chapter 3 quiz. This topic of related rates is not going to be on that quiz, so you don't have to worry about that. Okay, maybe we'll spend the last 5 minutes talking about what will be on that quiz, and we'll get back to related rates on Tuesday. Okay. So what will be on the quiz? This is quiz B. No, it's quiz. Oh no, it is quiz B, isn't it? Yeah. We're gonna have stuff like limit of difference quotient. Sorry, I used delta x this semester, didn't I? Remember that? This has been a while since we've done this, okay? So this might show up on the quiz. Okay. This is the derivative of a function. This is the derivative definition. This could show up on the quiz for sure. But there's also there's also going to be the differentiation rules, the shortcuts. Go ahead.
I have a quick question.
Of course.
In the other meeting before the snow days, you said that you might just ask questions about the definition of a derivative. So you're gonna be like, what is it? Or like, would those be like multiple choice, or would it be like written answer? Or
yeah, I might do sort of like a multiple choice or a true false kind of section, which is like conceptual questions about like getting at the ideas. So when I say this is going to show up, I don't necessarily mean that you'll have to actually compute a long limit with the algebra involved. I might just ask you about this definition, right? So let's review what this means, okay? Because that's, I think, important. This is the secant slope. Right? That expression on the inside of the limit, just the part on the inside, which is what's called the difference quotient. That part is the slope of a secant line, right? Because if you're drawing, if you have your x here and you have some change in x, some delta x, right? Then you've got your other point over here. And that expression that is in red over there literally is calculating the slope of the line that passes through those 2 points. That's exactly what that expression on the inside is doing. It's calculating that slope. And then the idea then is that with the limit, What you're doing via the limit is having this part shrink down. So this point is approaching the other one along the along there, and you get this sequence of secant lines that approach. They sort of go like, like here's a closer one, here's a closer one, here's a closer one, and then they approach this tangent line. Right, so that's why the entire thing altogether produces the tangent slope. Okay, it's because you've got your secant slope. You're doing a limit of the secant slope, and that gives you the tangent slope. Anyway, that I think is the main thing I want you to understand. And then I might ask you about on sort of it could be multiple choice, it could be true, false, it could be short answer. I might ask you to just write. I went like this, but it'll be in class. So write an explanation or draw a picture, something like that. Okay. That'll be on there. But then we also have differentiation rules, the shortcuts. So this is where, I'm just going to give you like probably three or four functions. I'll just give you some functions and have you take the derivative. Okay. We also have implicit differentiation. Okay, so there'd be one of those. And then we have linear motion, which is one of the early applications we studied, right? Oh, another thing. So this is, sorry, before I move on, this is position, velocity, and acceleration. Another thing that we studied in here is graphs of f and f prime, right? Remember those problems you did on the worksheet that were like, here's a graph, here's a function, now draw the graph of the derivative of that function. Or here's two graphs and identify which one is the function and which one is its derivative, that kind of thing. So that'll be on the quiz too. I think that's pretty much it for chapter 3 topics. Logarithmic differentiation won't be on there, but the derivative of a logarithm could be on there. Okay, the other thing I'll say I won't put on the quiz is I won't put inverse trig functions on the quiz. Okay. I tend to downplay the inverse trig functions during Calc1. They become very important during Calc2. I don't want you to experience inverse trig function fatigue. So, we'll do plenty of that next semester or over the summer if you guys take it with me over the summer. Okay, that's it for today, folks. See you next time. See you next week. I see your question in the chat, Hannah. So we used proof that we know a particular method. We use a different method. Oh, yeah, no, that's fine. So like, are you talking about in the when you're just doing derivatives of functions with the shortcuts? I think what you're asking. Oh yeah, sure, that's fine. Yeah, so that would be in this area here. No matter what technique you apply, as long as it's correct, it's fine. So like you can go about breaking down the functions and then you applying product rule and quotient rule and chain rule. As long as it's correct, as we've seen, there's often more than one way to do it. Like we just talked about the 1 over L versus L to the -1. Are you going to use the quotient rule or just the power rule? Either of those are totally fine. Okie doke.
I have a question, or do I wait until your office hours?
Is it more of a like a longer question potentially?
Yeah.
Sure, let's do office hours. I'm gonna just go grab a cup of coffee and I'll be back shortly.
Okay.
Does that work for you?
Yes.